So this is a kilogram reaction in toluene of methyl methacrylate, and you can see again that's that colour there. And everyone seems a bit worried about the colour you get from copper chemistry, but it's not a problem at all. So then that's a kilogram of PMMA that came from that reactor, and you can see it's pretty white. And then we scaled that up in my first spin-off company, and this is actually a pilot plant doing 150 kilograms, essentially exactly the same as this reactor. It's pretty much stirred tank with jacketed heating, which is this bit here. And the kinetics for that was fantastic, actually, almost the best kinetics we got. So another message is that things actually work much better usually when you go to larger scales, as long as you're careful. And we had a lot of fun with that. So these are some early papers where we started messing around with bioconjugates and what you would probably call nanomedicine now. And so we were polymerizing these to make alternative pegylation agents with an aldehyde on the end, and alternative pegylation agents with maleimide on the end to conjugate to different amino acids. We had a very early paper on making synthetic glycopolymers, which we called neoglycopolymers at the time, where we were using different click chemistry to put on different sugars. But all of these polymers were being used at, in organic solvents, see 70 degrees, 80 degrees in organic solvents. And I'm not going to really talk about this one, but this sort of started the way that when we showed that you could do this type of chemistry in very complex aqueous solvents. So Guinness is, we would consider a very complex solvent. It's about 6% ethanol, about 94% water, plus loads of sugars and all sorts of junk in there. So I'm not going to talk about that, but that really then sets the scene for what we wanted to do, moving away from these conditions to these conditions: subambient temperatures, fast reactions, complex solvents, not purifying anything. And then that also moved towards doing the reaction without having to degas or deoxygenate in any way. And the traditional approaches, as you all know, are using vacuum lines, Schlenk lines, or glove boxes. And a number of people were working in this area, and still are, which I've got down at the bottom. But typically they're adding something. So they're adding something to remove the oxygen before they do the polymerization. So you could either add a reducing agent or enzymes or ascorbic acid. And typically, especially if you're making polymers for biological applications, but pretty much all applications, I guess, you don't really want to be adding things that you don't need to add. You want to be removing things. So every time you add something, that means you've got to purify it more. It adds complexity, the potential. And believe me, when in my transdermal company, all we're trying to do all the time is remove things from the formulation, because everything you add means the regulator is going to ask questions. So we were thinking, well, can we do it without using an external stimuli? And it wasn't just a copper chemistry, so people were doing what you probably know as PET raft, and certainly in Australia. So a lot of these papers were coming out, a lot of Australian influence. So you see Cyril Boyer, as you know, in Australia, is very active in that. So there's Cyril here, but also Justin Cooper White with Julian Rosselgon was working on this, and then Robert Chapman when he started his work with Cyril Boyer, and then took that back with Molly Stevens. But all of the time, they're adding something, either something to absorb light, like a very high, highly absorbing organic molecule, or they're adding enzymes. And this is our first paper in this, and so this was really the first contribution of Evelina, who I think is in the audience, and this was a collaboration with Kelly Valonia. And what we're going to show you now is that actually you don't have to add anything. All you have to do is fill the reactor up to the top. And actually, in an academic lab, we're generally working with round bottom flasks or reactions which have got a lot of space above it. But as you saw earlier when we did the scale up, the headspace is much less. So when you do a large scale reactions or scale up, you don't have much of a space. You don't really want to waste that volume. And so you're normally filling up almost to the top. So this is our reaction we're going to do here. We're going to use copper wire. It's going to be the source of copper, not copper 1 bromide. We're going to be doing for the next few slides an organic solvent, DMSO, and the ligand is hexamethyltrin. And we had a little bit of copper too. And the reaction here is methyl acrylate, so it's an acrylate, not a methacrylate. That's quite important. We've got the same initiator, tertiary bromide with an electron withdrawing group, and we're going to make this polymer. First, note that we're not using a Schlenk tube anymore. We're doing a vial. This case we are degassing, but note the colour. The colour is pale blue, and the pale blue, pale green is coming from the copper 2, not the copper 1. And we've got an aliphatic ligand, not an aromatic ligand, which means it's much less coloured. And you can see here the wire that's wrapped around the stirrer. Oh, right, there you go. So when we did that, so focus on this one. So the first reaction is in this file, and we saw a very high, good conversion, almost 100% by NMR, excellent dispersity, not quite the initiator efficiency we would expect. And you see this green color was not copper 2 that we added. The green color is the oxidation of the copper wire with the oxygen that was in this space. And then we reduce that space. Basically, we've done just take a smaller vial. The headspace is smaller. There's less copper 2 formed. And you see that the initiator efficiency has gone up 84%. Dispersity is still pretty good. Conversion is pretty good. And if you go one step further and just essentially do exactly the same reaction, just use a smaller vial, you see straight away from the color, it's a paler green. There's less copper 2 formed. The reaction's still taking place in a very fast time scale. We get quantitative conversion pretty much by NMR. Less than 1.10 dispersity. Remember, we were getting 1.25 early on and thinking that was good. And we have now 100% initiator efficiency. And all Eveline has done there is we've not degassed. All we've done is filled the vial up to the top. And so just by removing that headspace, no additives, you get pretty much perfect polymers, which we published a couple of years ago. And just to show you that you can actually compare the no headspace reaction with the freeze pump thaw, and the polymerization of the molecular weight distributions are identical. I mean beautiful. No tail to low molecular weight, no bimolecular termination, pretty much full conversion, identical molecular weights, and dispersities as good as you'll get anywhere. Not only that, we want to be able to do chain extension. So to do chain extension, we need very high-end group of fidelity. So when we analyze this by MALDI, and I'm not sure if you're all familiar with MALDI, but essentially we've got here, this is 2 different DPs, DP25, DP26. And that polymer is 25 methyl acrylates with 1 bromine and 1 initiator fragment. And you see nothing else in between. So that means every single polymer is initiated by the same group and is terminated with bromine. And this is DP26. And that means once you've gone to 100% conversion, you can add a second monomer and you get a block copolymer forming. This is methyl acrylate, but this is 2 different acrylates here. And you can get relatively high molecular weights. So you start to see a bit of a tail when we get to about 80,000, but even that, the dispersity is 1.13. And so you see these very, very narrow dispersities. I mean, what I really like about this is not just the 100% end group fidelity. And remember that, because this should not happen. We have fast reaction. We've got allegedly a free radical reaction, so we should have termination, but we don't. Right? And I'll come back to that in a moment. And because we have no termination, we can get pretty much the B block, the whole molecular weight distribution shifts. Now, that's not always the case in a lot of chemistry that you may have seen with living radical. Quite often with AB blocks, you'll see a tailing, significant tailing from the AB across the A, because quite often you have contamination of the block copolymer with the homopolymer. And this system we think is pretty good. So Evelina showed that you could do it in both organic solvents, or you could do it in water. You could use 4 different monomers, methacrylates, styrene, acrylates, and acrylamides, and water-soluble acrylates as well. So various temperatures, various solvents, and basically the chemistry is quite robust. But what I was pretty keen on is, well, so you can do this reaction without deoxygenating it. So how much oxygen is actually in our reaction? And Evelina will probably remember many lively debates about, well, I'm not really interested in doing this unless we can measure the amount of oxygen. And then we found this little machine, and I'm going to recommend this, that every lab should have one. So this is a method of measuring oxygen concentration in gases and liquids. This is from the manufacturer's site. So it's sold to measure the oxygen concentration in rivers and streams, basically to see if fish can survive in rivers. Costs you about £2,000, I believe. I can't remember exactly, $2,000, $3,000 maybe. So it's not very expensive. And it doesn't just work in water. You can buy one where the sensor is embedded in a needle, and the needle will go into any organic solvent you want. So you can just dip it in a liquid or gas, and it instantly tells you what the oxygen concentration is. Really could not recommend this little piece of equipment more highly from this company in Germany. And once you do that and you go and revisit what I've just showed you, when we do the 20 mil headspace, you can see that the oxygen level shoots down, and after about 10 minutes it finishes. It doesn't go to zero, which is interesting. But then when we do those other reactions, you see as we have less oxygen to start with, less oxygen in the air, that can go into the liquid and it gets consumed. And so with no headspace, we see a much more rapid, it goes to zero, and it's taken about 5 minutes to remove all the oxygen. So although we don't add anything to deoxygenate, the copper wire is removing the oxygen, because the copper wire is getting oxidized to copper 1. The copper 1 is disproportionating to copper 0 and copper 2. And so all the oxygen ends up turning copper into copper 2. Now, contrary to classical free radical kinetics applied to living radical polymerization, you might think, if you believe much of the literature and famous polymer scientists, that as you increase copper 2, you should be slowing the reaction down, because copper 2 should be a deactivator, but actually that doesn't happen. And then once you've done that, you can start saying, well, what do I need in that reaction to remove the oxygen? What's removing the oxygen? So if you just take copper 2 with a ligand, you see a slight decrease in the oxygen, but nothing that's going to make any difference really to your reaction. You start adding copper 0 and copper 2 with a ligand, you start to see the oxygen is coming down. You put in some initiator, so the initiator can actually consume. That's not a good thing, because your initiator, you want to initiate polymerization. You don't want your initiator to react with oxygen. But when you put all of the things in together, you can see that the by far the fastest is when you've got everything there, and it is indeed the copper 0 that you want is to take out the oxygen, turn itself into copper 2. And only with this little gizmo, this little £2,000 meter, that we would manage to be able to find that out. And then we wanted to expand that to light. So this was a paper published last year. So can we do oxygen tolerant chemistry with light? So now the reaction is slightly different. So instead of using copper wire, we're using copper 2. We're using copper 2 with hexamethyl-tren, same ligand. We're still polymerizing methyl acrylate. We're still using DMSO. So here we're using a relatively hydrophobic monomer to give a hydrophobic polymer, which we'll switch in a moment when we switch to water. We're using this very inexpensive £10 nail varnish curer that we buy from eBay, which I think we were the first people to use these, but I think they're becoming quite common in polymer chemistry labs at the moment. They're very good. They've got a very broad band UV at 360. So when we use that, we can either just eliminate the headspace, or we can deoxygenate. And in both cases, we get exactly the same results. So you don't need to deoxygenate, you can just remove the headspace. So again, note the dispersity is less than 1.10. The conversion is full conversion, and the molecular weight is pretty much exactly what we get, and there's no difference between deliberately removing the oxygen with nitrogen or argon, in this case nitrogen, or just carrying on by filling your flask up to the top. And also the shape of that dispersity is what I think is the most striking thing. No tail and no biomolecular termination. And then this is quite versatile, so we can then make relatively high molecular weights. So this is polymethyl acrylate going up to 50,000, 1.12 dispersity. We can do tertiary butyl acrylate, we can do fluorinated acrylates, we can do water-soluble acrylates. And so hydrophobic, very hydrophobic, hydrophilic. And then what we did, or Evelina did, was thought, well, how can we use that? So now this is that same nail curer. So this is the size of your hand. Your hand is designed to fit, well, the machine is designed to fit over your hand. And in here are little inserts that you might use for HPLC or GPC. These are HPLC inserts. And so you see a little bit of polymer solution at the bottom. So here we're doing 15 reactions at a time. And when we start to do that, we get this data. So you can use 200 microliters, 1.07. You can do 40 microliters, 1.08, 20 microliters, 1.11, and 5 microliters. And so it doesn't really matter what size you do. So here this is full of air, but the surface area to volume ratio is very small because it's a tiny volume. And again, we're not deoxygenating, just filling up these tiny little vials, put them in the inexpensive light curer, and the dispersities are all pretty much the same. A little bit broader when we go to 5 microliters. So we can scale down, we don't have to remove oxygen. And so then we can get higher DP. So now we've gone on the intermediate volume. Now going up to DP 400. So the dispersity is still pretty good, less than 1.20 and 25,000 molecular weight. Remember, we're not deoxygenating this at all. My slides just frozen. I'm talking too fast for my slides. It should catch up in a moment. Oh, here you go. And so then, again, this is very versatile for different monomers. This is just to show you the versatility in monomers without deoxygenating and photoinduced, remember. So tiny little peg chain, big peg chains, T-butyl chains, fluorinated chains, styrene, with a different initiator here with the fluorinated monomer, and lauryl acrylate. So we do a lot of work on dispersants, which you'll see in a moment. And lauryl acrylate is very hydrophobic polymer. Again, we get, I think, perfect polymers, so which we see from the MALDI. So this is the MALDI distribution all the way across the molecular weight distribution. But then when we zoom in on DP26, DP27, there's nothing else initiated. There's no evidence of any termination whatsoever. You've just got DP26, where we've got the initiator on one end and the bromine on the other end, and DP27. So just no termination. And we can exploit that for making very nice block copolymers. So we've done that in organic solvents with copper wire. We've done that in organic solvents with light. And the next paper, which is going to catch up in a moment, is with water. So we wanted to be able to polymerize in water, and we wanted to be able to polymerize in water without deoxygenating, and we wanted all the polymers to be perfect. And at the same time, we don't want to purify any of the reagents. We don't want to remove inhibitors, we don't want to distill, which was completely the opposite of when I was doing anionic polymerization. So it's still trying to catch up. The next slide you'll see has got a graphical abstract on it, so it's probably got tell you what's going on here. So excuse me, my computer is now trying to catch up with what I'm doing. Okay, that's not good. So just bear with me. It tells me my PowerPoint is not responding. So what I'm hoping to tell you is about a paper that's just been just coming out in chemical science. I'm going to have to restart my program, right? I think. Not quite sure what goes on here. Right, so at the picture you can see there, all you Australians, do any of you know what that is?
England.
No, it was Hamilton Island, in fact. Right, so we're back. So that was when I was in Cairns a couple of years ago. Right.
I'm surprised that you had such a good weather on Hamilton Island, because the weather in Cairns, if it was macro 2018, it was pretty bad, I would say.
It was pretty bad, but we went there the week afterwards, so it got a bit better. Right, here we go. So now we want to do the reaction in water. So this paper is out actually last week in Chemical Science. So again, this is another chapter from Evelina's thesis, which she's just finished. And so what we're going to do here is, again, it's that little gizmo, and we're going to do it in water. And in water, it's particularly efficient to self-deoxygenate. So before I tell you about what Evelina did, I just want to introduce you to this chemistry, which you may not be familiar with. So when we use water as a solvent, and we use copper-1 bromide with an aliphatic amine ligand, it's completely unstable. So as Chris Matiszewski will tell you, ATRP catalysts are unstable in water. And what happens in a matter of seconds, you disproportionate copper-1 to copper-0 and copper-2. And the copper-2 in water is blue. It's like putting some copper sulfate in there, so it's copper hex aqua, copper-2. And these little red bits of things are copper-0 that's been produced. And we're going to hopefully show you that in real action. So I don't know what you can hear at the moment, but you either hear Paul Wilson's voice or my voice. So he's going to add some copper-1 bromide to this solution in water. And as soon as he adds it, you'll see that the color will start to go blue. So he's added copper-1 bromide, which is white. And within 10 seconds, a disproportionation reaction is occurring. And you get copper-2 forming, and there's a little bit of black stuff around there, which is copper-0. After 30 seconds, the reaction is complete. And it's at that stage we add the monomer. Right, so I'm not sure what you heard there, but we added copper-1 bromide, which is white, to a solution of ligand in water. And within 30 seconds, it disproportionated to copper-0 and copper-2. So there is no copper-1 left at all. And if you change the ligand from hexamethyltryptophan to PM-DETA, you'll see. So now all we've done now is change the ligand to PM-DETA. So now you'll see, before Alex has got a chance to press a button, it's gone blue. Right. So what you had there was that reaction takes less than a second. So you get full disproportionation. There's no copper-1 left at all. This is copper-0 and copper-2. And that always happens in water with these ligands. And then we add the monomer after that's happened. And so when we do that, all of a sudden we can start to do acrylamides. So acrylamides and polyacrylamides are only really soluble in water. And so the pre-disproportionation here. And then the reaction's been done at 0, and we're doing the reaction over a short time period, and we can get relatively high molecular weights of polynipam. And then Glenn Jones came along. Glenn's actually now a postdoc with Eva Hart, and what he showed, you could do that with acrylamide itself. So here we're polymerizing acrylamide, and you can't really do acrylamide by ATRP. You can probably do it by raft if you're good at raft. So Seb Perrier can do it by raft, probably CSIRO can do it by raft, probably not many other people. You have to be pretty good at raft to do this, but ATRP doesn't polymerize acrylamides. So here, and especially acrylamide itself. So Glenn showed not only can we polymerize it, the reaction takes place in about 2 minutes. The conversion is more than 99%. There's no monomer that we can see by NMR, and the dispersities are about as good as you can get. And not only that, if you look at the shape of the shape of the molecular weight distribution, it's pretty much perfect. Now this should not happen, right? So when we polymerize that, you see that the kinetics is less than 2 minutes, but then a bit later on, you can add your second monomer and you can get a perfect block forming. So for those of you familiar with living radical polymerization, you'll probably be aware that you're told that you cannot have very fast reactions, because if you have very fast reactions, you have a lot of radicals formed. If you have a lot of radicals formed, you have termination by radical-radical reactions, combination or disproportionation, normally combination. And so this is something that shouldn't happen. And when I was in Cairns actually and presented this, Craig Hawker, another good Australian, was in the front row, and he said to me, how do you explain your results, Dave? Because that shouldn't happen. And I said, well, there's 2 explanations. One is that I'm lying to you and everything you're seeing is just being fabricated, but I don't think that's true. Or the mechanism is incorrect, but I don't know what the mechanism is. And fortunately for us, at the start of this year, Nick Ballard, who's a graduate of Warwick actually, came from Stefan Bond's group, published this paper in ACS macro letters. And again, this was fantastic, because what he starts in his paper, he says that an extreme case reported by Jones, which is the paper I just told you about, shows you that the reaction is really fast. And he says some simple calculations show you how amazing that result is. Well, when somebody tells you something's amazing, they're either telling you they don't believe you, or they're telling you you've done a super good job, right? It's about 50-50 either way. And he tells you that this is important because there's normally a compromise between reaction rate and reaction control. And so the commonly held belief is the faster the reaction, the less control. And I've just showed you something that goes as fast as you can go, and we get perfect control. So it doesn't make sense. And then his conclusion is that if you use classical reaction kinetics, which of course people like Chris Matuszewski uses, it means it doesn't work. Right? But contrary to that, if you use something called probability density function theory, that I'm not going to go into, but you need to read the paper to find out. He gave a great Zoom talk to us a few weeks ago from Spain. It says that this explains everything. And not only does it explain us, it means that you can disregard this myth, which has been built up by classical reaction kinetics. And now you can do, if you get it right, fast reactions, which means you can get a good degree of control, which was thought to be impossible. So we're very pleased that the explanation is that we were telling the truth and not lying, and that the commonly held belief in the mechanism was not right. So then if you take that and go back to what Evelina's done, so we can self-deoxygenate in water using copper 1. And what was interesting that she first found out, she wanted to know what was happening with the copper. So if you do electron microscopy of copper 1 bromide, it looks a bit like this. But if you start taking samples throughout those disproportionation and the polymerization reactions, you see that it actually becomes really very different, actually, and it's quite interesting that you get these dendrites forming at some point. You get like growth with little nodules, and the copper species that you form has got a very, very high surface area. And I'm not going to go into too much detail, that's in the paper that's just out. But this, I think, brings it home to you that if you look at the surface of copper wire, it looks like this. So it's not smooth, it's a bit rough. But if you look at the copper zero that's formed in our reaction, remembering that you started from an atomic scale, it's totally different, which you can then see by different spectroscopic techniques as well. So by applying that, you can then just do that same disproportionation, pre-disproportionation in water, and all those monomer types, but now these are all water-soluble monomers, acrylamide, dimethacrylamide, NiPAM, hydroxyethyl acrylamide, and morpholine acrylamide. We're now using this water-soluble initiator, which actually turns out you don't have to do, but essentially it's the same as a tertiary bromide with an electron withdrawing group, and all the polymers work very well. So that just summarizes that. So you can do self-deoxygenating. You don't have to deoxygenate. The copper takes it all out, and you get very good dispersity in good reaction times. Kinetics would generally look like this. So we're following this reaction here over about 10 minutes, and we're just watching the monomer disappear and the polymer grow in here. So you've got a polymer and a monomer peak there, and the molecular weight distributions remain really, really very nice. So very rapid. And then let's compare. So when we use our oxygen monitor, this is what we were talking about before. We use different lengths of copper wire, and we get faster rates of oxygen depletion. And we're typically with this red one, so we're typically using about 2 to 4 minutes for the oxygen to be depleted in an organic solvent. But in water, it's 5 seconds. Right, so in 5 seconds, all the oxygen is gone, it's 0. So just by adding the copper one, which disproportionates to copper zero, the copper zero reacts with the oxygen to go back to copper one, the copper one disproportionates back to copper one, and that circle is so fast, you end up with a little bit of copper 2 being formed, and the amount of copper 2 is from the oxygen that you had that you didn't deoxygenate, and in 5 seconds you're good to go. And it's definitely the ligand. So if you put copper 1 bromide just in water, nothing happens to the oxygen level. You can change your ligand all the way from BP to the aliphatic ones, and in every case the time scale changes, but with all of the ligands that we've got here, in less than 5 seconds all the oxygen has gone. So nothing added, it's self-deoxygenating from the reagents that we would use anyway. Then we can turn that to flow. So again, we started this work with working with Tanja Junkers when she was still in Germany before moving to Monash, but this is a work of Arkadios. So Arkadios now wants to do this reaction in a flow with UV light, with copper 2, as we go down a tube, basically. This is our setup. So we're just using syringe pumps to have different ratios of our reagents, and we've got HPLC couplings in there, and we're using this box, which is a bit like a microwave box, but it's been designed to crosslink, so it's about £1,000, and our tube's inside the box, and then it comes out, and then we collect our samples here. And so what Arkadios did was showed that you can change the residence time, which means a different flow rate. The residence time is anything from 15 minutes to a few hours. The conversion, the longer you leave it in, the more conversion you get, but you want to stop at the optimum conversion. You get extremely good linear first order kinetics, and you get good molecular weight control, and you get very good dispersities. That's not good. It seems to have frozen again. Let's hope it catches up. Here you go. So then what we've got here is our reaction now is the light system in DMSO with a hydrophobic monomer, and we get higher molecular weights using that flow system. At the same time, we can get extremely good end group fidelity. And now how we use this in the flow system is we have this as our product, but we want to get rid of the bromine and put something useful on. So here we're doing a thiol reaction. So you're probably familiar with thiolene chemistry, but here what we're doing is a nucleophilic substitution of the bromine with a thiol. In this case, we've used thioglycerol. And so in the flow system, we can put that and we can replace the bromine with the thiol. And this puts, in this case, a diol on the end of a relatively hydrophobic polymer. That's a dispersant. So for dispersant, you need, if you want to disperse something in an oil, which we often want to do for automotive applications, we want to put something hydrophilic here and hydrophobic there. And we can follow that. So we have pretty much 100% conversion of our bromide into our diol. So that's how we use that with this thiobromine substitution. Now, I'm going to rush through a few things now because I want to stop in 5 minutes, but I want to highlight a few other things from the people who are probably watching this. This is quite recent as well. This has just come out last week, or probably last week, I think, maybe this week. So this is work of Konkai Ma, who's a second-year PhD student. And I don't know if you're familiar with this, but we wanted to use AIE, association-induced emission, which is where normally when things fluoresce, as you increase the concentration, they quench, and so it stops fluorescing. With something that's an AIE, it only fluoresces when it aggregates. So if it's not aggregated, it doesn't fluoresce. If it aggregates, it does fluoresce. This is a very, very topical area, especially in China. So with a guy called Benzong Tang. So this was we had a collaboration with Benzong Tang, who's I would imagine will win a Nobel Prize for this at some point in the future. So what we've done is we've taken a very standard AIE, which is this tetraphenyl ethylene. We've made the tetraphenyl ethylene with a single hydroxy group. We've turned that into an initiator, and then we've used our copper wire system to polymerize off monomers that all contain the TPE group on the end. And the TPE group does not fluoresce. However, when it aggregates, these twist a little bit. I'm not going to go into the details on that. And when they twist, it fluoresces. So you know it's aggregated because it lights up. If it doesn't light up, it's in solution. So using that initiator, as you might imagine, you can freeze your computer again, but we'll see if it catches up with me. So then what we're going to do is polymerize off a whole bunch of different monomers, as you can imagine, that I've already shown you before. So on the next slide, we're going to see methyl acrylate, ethyl acrylate, T-butyl acrylate, benzyl acrylate, and PEG acrylate. And as soon as you start putting T-butyl acrylate, which is a monomer that we like quite a lot, the T-butyl acrylate in this R group can be hydrolyzed off. There we go, good. So once we've got this, we can hydrolyze that off very, very easily to give you acrylic acid. So then with acrylic acid, you can have TPE with very hydrophilic, or you can have TPE with a very hydrophobic or moderately hydrophilic. And you can make block copolymers. And then once you make a block copolymer, specifically this one here, or this one is the other way around, you've now got hydrophobic with a very hydrophobic, but we take off the T-butyl to give basically polymethyl acrylate and polyacrylic acid. Here we have polyacrylic acid and polymethyl acrylate. And once you've got those, they will aggregate in different solvents, water or organics. And then this is what you get. So there's a lot of data on here. This is in the paper, but you see that once it's dissolved, it doesn't fluoresce. And once it aggregates, so all we're doing here is changing the amount of water in the THF. And once we get to the right balance, it starts to aggregate. And when it aggregates, it lights up. When it dissolves in the molecule, it doesn't light up. We haven't invented that. And that's Benzong Tang and AIE. But here now we've put it on our polymers and showed that the effect will still work. And then once you've got the acids, you can have a pH responsive behavior. So that means that as you protonate, as you make a salt out of the acid, you make it more water soluble. But then if you go too far on the pH, you can reverse it. So there's an optimum fluorescence that you get with pH. And what we use that for was for bioimaging. And again, I'm not going to go into the details of that. That was done mainly with our collaborators. But what we're seeing here is that we have polymers are low cytotoxicity. They're very excellent photostability, because one of the problems with bioimaging is a lot of reagents photo bleach. And what we're doing here is we want to know when the polymer is aggregated, it lights up, and when it dissolves, it doesn't light up. So it's sort of telling us where the polymer is, which is in that paper. Right now, this is another area which should just be published very soon by another PhD student with Athena, where we use the polyethylamine. So you might be familiar with polypropylene glycol, or PEG, and polypropylene glycol or PEG will normally have a hydroxy group on the end, and they've been used quite a lot to make macro initiators. And if you have an ester group there, you make a block copolymer with an ester link in the middle. The problem with ester links are that they're hydrolytically unstable, and so, but using amides as initiators has been difficult because it leads to a lot of termination. But with the chemistry that we're showing you now, you can use amide monomers. So if you can use amide monomers, why can't you use amide initiators? So then what we do is we just amidate the jeffamine to polyethylamine to make very similar, but it's different because we've got an amide instead of an ester, and then that's more hydrolytically stable. And then use our aqueous system, because we want to polymerize in water, to make a block copolymer, which is essentially PPG or PPG PEG NIPAM. All works very well, otherwise we wouldn't be showing you. So we can make a whole range of diblocks and triblocks polymers, which have now got NIPAM. NIPAM's got an LCST, so when we go above about 38 degrees centigrade, that's going to become insoluble. So now we have this diblock or triblock, depending upon what the polyethylamine is, with a hydrolytically more stable amide as opposed to an ester. People in certainly biological applications are always a bit worried about esters. Everything's amide now. There's no ester groups in this at all. We've got ethers and amides and amides, and we have an LCST amide there, and that shows very good LCST properties, which will hopefully come out in the next few weeks, I think. Now, I know Ellis is on this, so I'm going to just take 30 seconds on this one. So this came out at the end of last year, and so this is exploiting the ability to have no termination. So now we've made a fluorinated initiator, a very small initiator. It's not a polymer. We've polymerized now an IPA with our light system. We've polymerized off T-butyl acrylate. Because we can get very, very finite control, we get tiny DPs, which is quite difficult normally. We get almost perfect dispersities. And now we have very hydrophobic, very hydrophilic polymers. And then they'll self-assemble. And when they self-assemble, they'll give tiny, tiny domain sizes. So the domain sizes they self-assemble into are sub 10 nanometer, so 3 nanometers, which you measure by SACs. And what that does is we now can get, I mean, these are the lowest achieved by probably a factor of 10. And all because we can get this perfect polymerization, and we get very hydrophobic, very hydrophilic, very high Chi, very short DPs. So I'm going to probably finish there. This is so Yongguang, sorry mate, we scale up with light, and we also use this. I was going to talk about this green solvent, which Cardias has also done, which is used for it's a safe and green alternative to DMF, NMP, DMF, or DMSO. So on that, I want to thank the people, especially Evelina, who's contributed a hell of a lot to that, and the people that came before her, Athena, who helped Evelina out, but Glenn, who's now with Eva Hart, and Richard, who's a postdoc with Athena, Paul, who's a academic now at Warwick, he was involved with all the early stuff, Chan, who's a professor in Nanjing, and Chan did all the aqueous polymerization, Matt Laurel helped Arcadios with the flow, Konkai did the AIE stuff. Jiru did the work with the polyethylamines. Yongguang scaled up and Ellis did the very tiny hydrophobic polymers. And we're very thankful. Mostly for the funding comes from industry, but that's where I'm going to stop now. So thank you very much. And I guess I'll stop sharing now. Do you want to stop sharing, Jan?
Yeah, sure. Thank you, David, for this wonderful talk. And I have two quick questions which don't go into details on your science, but you mentioned in the beginning that a lot of reaction run much better on a larger scale. What would you attribute this to?
Okay, it's easy to purify. So if you're using a small reactor, the surface area of your reactor relative to the volume is massive. And a lot of the impurities come from the reactor. So certainly if you do an anionic polymerization, the surface of the glass is hydrophilic, and there's more hydrophilic groups on a smaller volume. So as you scale up, there's tiny effect from that. And also, if you want to purify something, so if you want to do anionic polymerization in toluene on a 200 liter scale, you just distill off 5% of your toluene and it azeotropes out all the water. And on a large scale, that's much easier to do. And on a small scale, well, you've got tiny syringes, everything just becomes, it's a surface area to volume mainly.
And my second question is, you also then, on the other hand, mentioned that, let's say, the less components a reaction has, the better, especially if you want to translate your research into industry or a product into industry. Could you maybe give some quick rules or key points for people to sort of know what to expect if they want to translate their products, what to kind of look at, what is the ideal reaction that...
Ideal reaction. So you don't want a reaction to take 2 minutes because you can't mix, but you don't want it to take 8 hours because that's longer than a day. So you want it to take about 2 hours to 3 hours. That means that somebody can come in, set it all up, do the reaction, clean it all out, then you can do one reaction every day. You want to do a reaction that is preferably refluxing or above room temperature, because removing heat is very expensive. So doing subambient is difficult. So reflux is brilliant, right? So then you know that the temperature in that is whatever the reflux temperature is. So then you just need a condenser. The condenser removes the heat. That's much faster. You don't want to have to purify your reagents because every reagent you use is impure. So that means if you add another reagent, it's got not just that reagent, but it's got the impurities in that reagent. And so then when you're doing a medical product, for example, we have to show that you get less than so many ppm even after it's been kept at a certain temperature for a long period of time, because the product will be on the shelf for maybe 2 years. That's where you have shelf lives. And any of the impurities you have, so for example, if you have, so an example for our transdermal patches, if you do ibuprofen, which is an acid, and you have any alcohols in there, which we do, then esters will form over time. You can't help it, right? And so you need to start with the lowest amount possible, and you need to have the least number of reagents in there, because then when you go to a regulator, you have to explain why everything's in there, and then you have to explain every impurity in every single reagent. So the less reagents mean the less explaining you have to do, the less expensive it is. I mean, it's just common sense, really. But we don't generally think about that when we're in the lab ordering stuff from Sigma and distilling our solvents, etc.
Biological applications, you want to stay away from copper, right?
For that, say that again?
But you would like to stay away from copper if you're going to put something in the body, if possible.
Not really. So copper is FDA approved. There's 12 proteins contain copper. It's FDA. It's called generally regarded as safe molecule by the FDA. You can have copper gluconoate. So copper 2 is a essential element for your well-being. If you don't take the right recommended daily allowance of copper, your nervous system will break down. In fact, the only thing dangerous about copper is if I have a copper brick and I throw it at your head, or if I have a copper bullet and I shoot you with the copper bullet. Copper is not toxic. It can be removed. In fact, it's completely the contrary. So it's just like cobalt and iron. So cobalt, if you didn't have cobalt, you couldn't have vitamin B12. If you didn't have iron, you can't have hemoglobin. Copper is an essential element. In fact, so if you want to compare copper with raft, thiols are generally extremely toxic. So the one thing you need to avoid, and this with everybody, is monomers. Monomers are much more toxic than any copper. So yeah, get that one out of your head. It's the monomer, residual monomer, that is a real problem, because the monomer does microaddition with amines, which is toxic. Copper is absolutely fine, and but you can remove it, because it's not part of your polymer chain. So that's a message for Australia there. Copper is not a problem. And some of the polymers that I showed you that just when we used copper 1, when we did in toluene, was with my company to make pegylating agents. They all went into clinical trials. So it's not an issue.
All right, that's positive. We generally in our polymers try to stay away from copper as much as we can, but we use it mostly for click chemistry, so we use strain promoted copper.
But it's built up from a myth. So someone will tell you heavy metals are bad. But okay, so some heavy metals are bad, but if you had no iron, you wouldn't be sitting there now, or cobalt or copper. Or if you don't, so metals are not intrinsically bad. Organic chemicals are intrinsically bad, but some are very toxic. Yeah, so it's a myth. Just the same way as the myth has been brought up, you can't do living radical fast because you get termination. I've just showed you can. But most people in the world think you can't because they believe what someone's told them. Someone's told you copper's toxic, but probably someone who does raft. And they have no evidence for that. They've just told you that because that's what they want you to believe. Just like Donald Trump every day tells fake news to the world.
There's also, I would say, there is a difference in what kind of copper you have, whether it's elemental copper or copper ions, because let's say
copper 2 you want. So copper 1 is toxic because copper 1 will oxidize phenols like Fenton's reagent, but copper 1 is completely unstable in water, as I've just showed you. So any copper 1 you have in the presence of amines in water, and there's lots of amines in your blood, it completely disproportionates to copper 2, and copper 2 is an essential element for you, literally. So and it is in about 12 proteins, without any of which you would not be alive.
That's true. So we have some hands raised, and the first one was Yun Huang. I hope I pronounced it correctly. So the floor is yours.
Yes, thanks. Hi, David.
Hey.
Hey. I was the student under Coach Ono, so I'm now in the IBM now. So yeah.
Yeah. So welcome. So Kaiji was a very, very good student, really very good, or postdoc actually.
Yes, very strict teacher, supervisor. Yeah. So I just want to ask, in the first system, actually, you were using the acrylate for all the experiment. Do you mentioned acrylate is very important for all your system. You are using copper 0 and copper 2 and acrylate, and also MEX strain. So what's the consideration about that? And yep.
So all the early work with pyridiniamines was with methacrylates. So the pyridiniamines are very, very good for methacrylates. Mm-hmm. What you probably know is the rate constant for propagation is much, much faster for an acrylate or an acrylamide than it is with a methacrylate. Coupled with the fact with a methacrylate, you have the problem of disproportionation for termination, not just combination. So in order for these very fast reactions to go, generally we use acrylates or acrylamides. So acrylamides are absolutely perfect because they have extremely fast propagation rates in water. And acrylates are very, very fast as well. But you'll note that I did have data for methacrylates. So we do have published conditions for methacrylates and for styrene, although then the reactions are a bit slower, generally a little bit broader dispersities. And so so water, we're pretty much always using acrylamide or water soluble acrylates.
Yep.
And it's down to the rate of propagation.
Yep. Yep. Yeah. There's also a second question is Kat?
Yes, sure.
Yeah, yes, sure. So the second question is about the comparison of the different volume of the air in your vial. So you're using a small special vial for that, and at 5 micron and 40 micron, which one is actually has a more contact area to the air?
So we don't. So typically we just use normal sample vials that you just buy. So you just get a vial that you would be using to make up an NMR, and so pretty much everything's just in a sample vial. So you get for then when I went to the smaller volumes, all we're doing there is we so it seemed like a lot of people around the world wanted to do things on small volumes and in open plate 96 well plates, which we also do, which I didn't mention today. So those are just inserts for HPLC vials. So you buy bags of 1,000 of them, and everything. So it all works, to be honest. So you don't have to fill it up. When you went down to 5 microliters, then the volumes are a little bit small, so it's easier to work at 100 microliters. But actually, most of the time, and we don't stir, so there's no stirring, and so it doesn't really matter how big the reactor is. So you just put it down there, and it works. But in general, if you went into my lab now, well, there's nobody in there, but if you in normal circumstances, you just see the reactions are just in sample files. And you have you may have seen those stirrers from ICA that have like 12 stations for stirrers at room temperature without any heating. You would just see vials blue tacked onto the stirrer, 12 of them, and they're just all going away doing their reaction. So all the Schlenkleins, unfortunately, because I love Schlenkleins, are falling into disarray because the students don't use them. And when I shout at them, say, is your Schlenklein working? They say, what's the point? We don't use it.
Yeah. All right, thanks.
All right. Any other questions from the audience? I actually have a couple of students from our group here as well. And now when you say they shouldn't use Schlenkleins, which I try to tell them they should, they will tell me tomorrow I should just go home and not waste their time.
Well, this chemistry, I mean, if you want to deoxygenate, you just buffer a few seconds with nitrogen. But as you see, you don't have to at all.
It's beautiful and really makes life easier, I would say, especially if you want to run 20 reactions at once, as most of your students do.
Also, and sample them all. The way that the guys in the lab do chemistry now is very, very different to how we did it 10 years ago or 5 years ago. So.
Yeah. And when you published the 2016 paper that Craig Hawker didn't believe you, that happens, how did you convince the reviewers that it's true?
Oh, so that the acrylamide paper. So one of the reviewers said you need more kinetics, and we said, well, we can't really, because we're doing it in water and we're already doing it at 0. If we go lower, it will freeze, and we can't sample faster, and so that's about as good as you can get, really. So we just presented the data without an explanation, and I don't see what's wrong with that. So we were not good enough to explain what we had. We didn't want to come up with a bullshit explanation just so we had an explanation. We knew, we were quite confident of the data we had. We got it repeated by many people. And even though when we started, your students get some data, you say, well, I don't really believe that, go and do it again. Okay, somebody else do it, and it just works. So we did not have an explanation. We knew the mechanism was wrong, that everybody believed. We knew that that was being propagated by fake news. We knew we didn't want to stop us doing that reaction just because someone had published a mechanism, because that's really dangerous. So if you believe always what's published, it would stop you doing that experiment. And it was essentially this guy Chan, who's now in Nanjing. So he just didn't bother believing the mechanism. Right? And that's a message I say out there, you know, don't believe all you read. More and more, the younger generation, you're much more aware of fake news and how people actually use it for positively. So sometimes fake news is out there by mistake. Sometimes it's actually being used as to try and positively influence you in a way that people want you to be influenced. But if you've got a conviction, you should do that. And if you have an observation that doesn't fit in with what should happen, don't think that you're wrong. It could be you're right. And in this case, that's what happened. And that meant that why would you ever polymerize and acrylamize in water with copper when someone's telling you that ATRP catalysts are unstable in water? Well, you just wouldn't. And hopefully, luckily, there were other scientists like Craig who's quite happy to say, well, okay, I believe your data, and I can't explain it either. And then luckily you've got other people that come along and who are clever enough to reanalyze your stuff and educate you, which is what Nick Ballard did.
Great. I think it's a great message to all of us here, just to believe in themselves and their own data, right?
Yeah. In IBM, we should start ADRP as much as possible. We do wrong.
Sure.
Yeah.
Is there anyone else who would like to ask a final question? All right. Well, thank you, David, again for giving us this wonderful talk and taking your time.
Thank you, David.
Welcome. Hopefully we'll see you in Warwick next year. Well, but we'll see about that when people are allowed to travel.
Yeah, also for those of you who don't know, David is organizing a great polymer conference every year in Warwick, and it's one of the best ones around the world, I would say. And it's, I haven't been myself ever before, but I heard a lot of good things about it, including a rock band or something like that. And a very nice polymer community.
Yes.
So we had to postpone it. It was going to happen in July. It's going to happen next Easter. And some of that's good. So in fact, Chris Barner-Cowlick, who couldn't make it in July, is now already signed up for next Easter. And so that's so some people will be able to make it and some people can't. So and hopefully everybody will be allowed to travel without having to worry about 14 days quarantine when you get somewhere. But and when you get here, hopefully you'll be able to play football, because we have a football tournament inside the and it's a real shame because the opening day of our conference was supposed to be the final of the Euro 2020, which of course is not taking place either. But okay.
Thank you, David.
Thanks, guys.
Thank you.
Bye.
Bye-bye.
Bye.